thanks a lot thanks a lot to the audience for joining us today again. Our speaker is Dr. Gerrit Maik Horstmann. Gerrit kindly accepted our invitation for this seminar. He did his Bachelor of Science in Physics at the University of Göttingen in Germany. His Master of Science in Physics from also the University of Göttingen from 2013 to 2016. And from 2016 to 2020, he got his PhD in Mechanical Science and Engineering from the Technical University Dresden in Germany too. So we could say that he just finished his PhD. For sure, he will have a successful career, a successful scientific career. And right now, he's a researcher associate at the Helmholtz-Zentrum Dresden-Rossendorf in Germany. Well, thank you very much, Gerrit, again, and please go ahead with your talk.
All right, thank you, Alberto, for the kind introduction, and thank you everyone for joining my talk. So today I'm going to talk about the main results of my PhD thesis, where I concerned myself with interfacial wave dynamics in multilayer systems. And thereby it was my main focus to better understand and predict the stability of liquid metal batteries. So at first, before speaking about fluid mechanics, I want to shortly introduce the main concepts of liquid metal batteries. I think many of you are already familiar with these batteries, so I will keep the introduction short. But just to give you a first idea, the idea is to fill 3 immiscible liquids into a tank, which can be cylindrical or also rectangular in shape, and must have electrically insulating side walls. And due to the immiscibility, the liquids will form a stratification like here due to gravity. And if we combine an ion conductive electrolyte and sandwich it between 2 suitably chosen liquid metals, one of lower density floating on top and one liquid metal or alloy with a higher density filling the bottom space, this 3-layer system will naturally form a simple concentration cell. So then we have a battery. For example, as in this example, we can use magnesium and combine it with antimony and some suitable molten salt in between. And if you operate at high temperatures, then everything is liquid, and we have a quite efficient battery, because the entirely liquid interior has many advantages. Because on the one hand, liquid-liquid interfaces have or allow for very high current densities. And the liquid interior naturally protects the battery from structural degradation mechanisms we know from solid batteries, which allows a long lifetime. Also an important point. But at the end, the most important argument is that the batteries are cheap, both in terms of power and energy, so they are competitive, which is why they are discussed today as strong candidate solutions for the stationary storage of fluctuating renewable energies. So it's a quite current topic, and they can be an important part of contribution to stop or deaccelerate the climate change. This is so the main topic, how we want to apply the batteries. But on the downside, of course, the batteries pose some challenges. They typically have low cell voltages, below 1 volt, and they need to operate at high temperatures, which both demands for intelligent thermal and power management. But for us, the most important point is that we have unknown fluid dynamics in these batteries. My battery group at the HZDR has identified several fluid dynamic instabilities which can occur in the batteries. So I am a fluid dynamicist. I made my PhD in this topic. So we are particularly interested into these instabilities. We have, for example, classical thermal convection, because we have Joule heating the electrolyte, which gives us a stable and unstable stratification in the anode and the cathode layer. We have also strong currents and magnetic fields giving rise to electrovortex flows. We have mass transfer problems or the Taylor instability, which is known from astrophysics. So it's a playground for fluid dynamicists. And we study these instabilities for two reasons. On the one hand, they can endanger the safety because if we have strong flow in one or both metals, they can destabilize one or two of the interfaces, which can provoke a short circuit we have as soon as both metals step into contact. On the other hand, they can be beneficial because they some harmless or controllable instabilities can improve the mixing, in particular in the cathode layer, which will improve the efficiency. So we want to do both. We want to keep the battery safe and want to increase the efficiency. This is why we study all these kinds of instabilities. And I have dealt the last 3 or 4 years with interfacial wave instabilities, which are driven by Lorentz forces. It's one particular topic. And these interfacial or Lorentz force driven interfacial wave instabilities are well known from physically similar aluminum reduction cells. So maybe most of you probably know that the aluminum production is a very energy intensive process. It is done in so-called aluminum reduction cells where we have a two-layer system. We have a molten cryolite floating on top of pure aluminum, which also forms a very similar two-layer stratification, and where it is well known that Lorentz forces can destabilize the interface. And this is critical because the energy losses are almost or mainly occur in the cryolite. So it is beneficial to keep it as thin as possible. But at the same time, if we reduce the height of the cryolite, then the cell is becoming more and more unstable. So here, the interfacial wave instabilities are a strong limiting factor. I think Peter Davidson has estimated that every millimeter of cryolite can cost a typical aluminum company $1 million per year of waste energy. So it is very important here for these cells to control interfacial wave instabilities. And in liquid metal batteries, we have 3 layers, of course, instead of 2, but a very similar physics. We expect there the same instability mechanism. And there are different interfacial wave instabilities which can evolve, but the most prominent is the so-called metal pad roll instability. And here I will give it try to give you a first intuitive feeling how this instability can arise here directly in 3-layer liquid metal batteries. So we can consider an idealized situation where we have a purely vertical charging current. So in practice, this is we cannot attain such a perfect current density, but let's just consider we have a perfect homogeneous current density in the cell, and we have some external magnetic field. So magnetic fields are always, both in liquid metal batteries or reduction cells, unavoidable because they arise due to the feeding lines. And they can be pointed in different directions, but we consider in this ideal case only the Z component, the vertical component of the magnetic field, because in this situation, the current in B is parallel, so we don't have any electrovortex flows. This is a situation which makes no Lorentz force in the first glance. So it's the most idealized situation, but even this setup here is inherently unstable, because in the battery, we have in the electrolyte layer has orders of magnitude lower electrical conductivities than the liquid metals. So due to this reason, many things happen if some of one or both of the interfaces are somehow displaced. if we consider a small displacement or a perturbation of the interface, then the current will be deflected. The current always chooses the path of least resistance, which in this setup is here at the left, where the electrolyte layer is thin. And we can split this deflected current into two parts, into the vertical current and horizontal compensation current. And this horizontal component now interacts with the vertical magnetic field and gives here some Lorentz force contributions here pointing inwards and here outwards the plane. And these current Lorentz forces will displace the interfaces. And in the upper part, it will push the interface here to the bottom, to the back wall. And then we have the same situation as before, but only phase shifted by 90 degrees. So the current, the induced Lorentz force density is deflected the same way as the interface, so that we in superposition always find rotational waves to be destabilized by these Lorentz forces. So here in the 3-layer setups, you see that both Lorentz forces in the upper and lower liquid point in opposite directions. So it is not clear in which direction the interface will start to rotate. I will address this question in a few moments, but it's just to give you a first feeling how the forces are coming from and what is the nature of the metal petrol instability. So of course, in practice, we have some further effects. We have inhomogeneous magnetic fields and so on, but this is widely regarded as the most critical instability mechanism, the vertical interaction of a vertical magnetic field with horizontal compensation currents. So when I joined the battery group at the HZDR at the end of 2016, I was confronted with the following results. My colleague, Dr. Norbert Weber, investigated the metal petrol instability numerically, in particular in magnesium antimony cells. And there he found that under realistic conditions, the upper interface is destabilized in and found rotational wave motion. You can here see the wave crest in the upper interface of magnesium antimony batteries. And this was the first result. And then he tried to understand or to predict the stability of these cells. And he applied a classical stability criterion, which originates from aluminum reduction cells, from 2-layer cells. And it is given by this formula where you have the product of the current, the total current and the magnetic field over the gravity, density differences and the heights of both of the metal layer, here of the electrolyte layer and the upper metal, because here this criterion is applied to the upper interface which is unstable. And this criterion, it's a dimensionless number, reflects the ratio of induced Lorentz forces by some interface displacement due to the restoring gravity force caused by the same interface displacement. So it's a key dimensionless number, and he applied it to his simulations and varied different or all the different critical parameters which are involved in this criterion. And he plotted here the normalized height of the electrolyte over the beta parameter. So 1 means here no wave motion at all, while 0 means short circuit, and between we have wave motion as shown here. We have some rotating wave. And if this criterion would be perfect, all curves would coincide, which is clearly not the case here. So we can roughly see 2 instability onsets. One onset here for the metal petrol instability, and the second onset where we find short circuits. But here, of course, it is not, it's far from being perfect, far from exact, which is no surprise because we have in the battery some different conditions compared to aluminum reduction cells. For example, this criterion is developed for very shallow cells, while liquid metal batteries are not necessarily shallow. And further, we cannot neglect interface surface tension at both interfaces because they are not necessarily large size in nature. So liquid metal batteries are scalable, and we have to consider all the different scales if we want to really understand the stability. And the most important difference is, of course, that we have 3 layers instead of 2. So I was wondering about one particular thing when I started. My first question was, why does the lower interface remain completely unaffected despite the fact that the upper interface is in strong motion? That was a bit counterintuitive for me. And further, Dr. Weber has compared the wave periods of the simulated waves with the eigenfrequency of 2-layer gravity waves and found some mismatch for small density differences. And so my first idea was, if the 2-layer theory cannot match the simulation data properly, maybe I can get better results if I perform a 3-layer theory. And that was the first thing I have done. I wanted to understand the coupling between those interfaces in the batteries. And therefore, I used the potential flow approach, which means that I neglect the rotational part of the flow, such that I can describe the velocity as a gradient of some scalar potential. This is an extremely drastic simplification because the Lorentz force is a rotational force. It has no potential. So strictly spoken, I cannot apply potential theory, but on the other hand, it is well known that in the leading order, the Lorentz forces destabilize classic gravity waves, which are well described by a potential flow. So I made a pure mechanical theory where I neglected all the magnetohydrodynamic parts. I neglected the Lorentz forces just to understand as a first try the mechanic coupling between both interfaces. So I have defined the following mathematical framework, 3 layers with different densities, different viscosities, and I also considered surface tension at both interfaces to deal also with capillary wave limit. And I defined the cylindrical coordinate system. And yeah, you don't have to face all equations here in detail. I just formulated all the conservation laws. So mass conservation, momentum conservation, with proper dynamic and kinematic boundary conditions, which are essentially determined by Bernoulli equations to account for this problem. So I have several no outflow conditions at the side walls, at the top walls, and I have some conditions which ensure that both interfaces are preserved and all this stuff. So it's a quite complicated system, but it is well known for comparable 2-layer systems. I have just expanded it to 3 layers, and I solved this problem and found some lengthy flow potentials for all 3 layers. So again, you don't need to read here everything. I just want to show you the structure of the solutions. So the potentials are described by products of hyperbolic functions in Z, Bessel functions in R as a radial coordinate, and simple harmonic functions in the azimuthal coordinate. And the important thing is here that I have 2 degrees of freedom, 2 wave amplitudes, while the potential of the second, the middle liquid, the electrolyte, depends on both wave amplitudes of the top and the lower interface. So all the coupling is arising in this potential, which is very different to the potential we find in 2-layer theories. And then you can see I have infinite sums of different wave numbers covered by the parameters m and n. And to show you how the waves look like, I have just plotted the first wave modes. So the first wave number determines the number of nodal cycles, and the second one, the number of crests and troughs in one nodal cycle. So for m equal to 0, we have axisymmetric waves, while the m equal to 1 and n equal to 1 waves, this one here, this is the most important wave related to the metal petrol instability. This is a large-scale wave which is usually most unstable and most dangerous to produce short circuits. So this is the wave of interest, but all these wave modes can be found, for example, if there is an earthquake and you have a glass of water on your table, you can see exactly these patterns, then often called Faraday waves, if they are excited by vibrations. So, but we are interested in this large-scale wave motion. And from my potentials and my boundary conditions, I could derive a dispersion relation where the coefficients A, B, and C depend on all the parameters of the model. So there are lengthy coefficients I don't want to show here, but the important thing is that it's a quartic equation which has two independent solutions, where it can be shown that one solution is always greater than the other one. So we have a fast mode, plus mode, and a slow mode, minus mode. And if I just apply the minus mode solution to the data from Dr. Norbert Weber, then you can see that now the theory can almost perfectly predict the numerical results. This was my first ever result I had, and made me feeling that I can really do something with the simple, very simple theory, or not simple theory, but this theory which does not contain any magnetohydrodynamics, which entirely neglects the Lorentz forces. But here the main benefit was made by including surface tension and not the three-layer, the inclusion of the third layer. So, but it was the first promising result. And then I went a step further and could also derive the amplitude ratio of these waves, which depends on the frequencies. And I had two frequency solutions, plus and minus. So I directly get also two solutions for the amplitude ratio, where I could show that the plus solution, there the ratio is always positive, while the minus ratio is always negative. Which means if it's positive, both waves are elongated in the same direction, while when it's negative, they are displaced in an antisymmetric way. So we have to distinguish between two wave modes. One is always symmetric and fast, and one is antisymmetric and slow. And this is important because this mode here can be dangerous for the batteries, can provoke short circuits, while this mode can improve mixing and cannot, if it's perfectly symmetric, cannot introduce any short circuits. So it was then my intention to kind of classify these modes to predict when the modes occurs under which conditions. So, and this was surprisingly complicated. Here I have plotted the amplitude ratio over wave numbers. So here I have the large scale wave motions, while here I have waves which involves many different crests and troughs. And I plotted these curves for different electrolyte layer heights. So here the inner solutions, there I have a very thin electrolyte, while the outer curves describe large electrolyte layers. And you can see you have perfect coupling when the amplitude ratio is 1, because then of course both interfaces are subject to the same displacement. And you can see two tendencies. First, you see that all the waves more and more decouple when the electrolyte layer is becoming large, which is no surprise, because if they are far away from each other, those interfaces, they cannot interact anymore. And you can see that the plus mode is all in all more closely coupled than the minus mode. And you can see, and this is the most interesting thing here, mode transition, which is, I checked different or three-layer theories describing oceanic waves. there I could never find these interesting mode transitions. So for large scale waves, the minus mode is more pronounced in the upper interface, but for small scale waves, it's more pronounced in, or equally pronounced in both interfaces. So there is a complex transition, and this transition occurs not only as a function of the wave number. I found this many times when making these plots for different parameters. And at the end, I succeeded to unify this transition dynamics by introducing two dimensionless parameters. We have one parameter which is a ratio of the restoring forces of both interfaces, and a second parameter which kind of reflects the inertia distributions in battery. And I could prove that we have almost always a state of perfect coupling if A is equal to B. And I further found for shallow electrolyte layers, which is practically relevant limit for liquid metal batteries, that there the plus mode is always perfectly coupled, while the minus mode is proportional to the coupling parameter A, which reflects the ratio of the two-layer eigenfrequencies of both waves. So again, no surprise, if both interfaces have the same eigenfrequency, of course, then they are highly coupled. They will naturally step into resonance. And all these results are reflected or by this butterfly plot, where I now show again the amplitude ratio over the coupling parameters A over B. And you can see, as I state, that for A equal to B, which is here, everything is perfectly coupled, while the minus mode decouples in both directions, while for small electrolyte layer heights, plus mode is always perfectly coupled. And if I plot the parameters for the magnesium antimony battery in this diagram, you can see, and I could on the one hand show that there also the slow mode, the blue mode is destabilized. And you can see that you have here extremely large amplitude ratio, around 30 between 40, which means here the upper interface displacement is almost 40 times higher than the displacement in the lower interface, which finally reveals why we only have seen a wave in the upper interface. So this is perfectly predicted by the simple coupling theory. We don't need Lorentz forces for this. So, but of course, this was a nice result. But then I need to check if my potential theory can really describe coupling in Lorentz force-driven interfacial waves. So I performed a numerical study where I used the multi-phase MHD solver mainly developed by Norbert Weber, which essentially solves all the important governing equations, so the induction equations, Maxwell equations, and Navier-Stokes equation. And I defined a coupling study around the state of perfect coupling and varied some parameters to vary the coupling parameter. And I found the following result. Here I plotted the period of the simulated waves against the coupling parameter A. So we can, if we have shallow electrolytes, we can neglect the parameter B. Then it's entirely determined by parameter A. So we can reduce the complexity a bit. And I found that first, the simulated periods are always in very good agreement to my predicted wave periods. But the interesting thing is that for A around 1, for highly coupled waves, I found in most times as a fast frequency mode, while for small and large A, the simulation was following the slow branch. So I found the coupling mode transition independent or as a function of the coupling parameter. What happens here is more obvious when we consider the amplitude ratios, because here you can see that indeed for small coupling parameters, we have dominant wave motion in the lower interface, and it's rotating slowly, while for large A, we have a slowly rotating wave where we have dominant amplitude in the upper interface, and in between, we have the fast modes, so fast rotating waves, where the interfaces are displaced in a symmetric way. So this was, maybe the most important result, because it shows that the coupling of Lorentz force-driven waves, the coupling is mainly due to pressure exchanges. So the coupling is perfectly described by this purely mechanic wave theory. We may neglect Lorentz forces in order to understand the coupling. And at the end, I applied the coupling parameter to many different liquid metal batteries which are discussed in the literature. And I found that all wave regimes are covered by different cells. So we can find the physics indeed in different samples of liquid metal batteries. And interestingly, the magnesium antimony battery is the most exotic case. It's the most decoupled battery, which was a coincidence. So in general, we cannot neglect the motion in the lower interface. In general, we have a coupled wave motion, and we have to consider the full three-layer dynamics. This was the main message of my first paper I published in 2018 related to this topic. So this was a pure theoretical result. And as a next step, it was my intention to study these waves also experimentally. This is, however, very complicated because magnetohydrodynamic experiments are not so easy to realize, because we have to operate at high temperatures, avoiding us to apply conventional measurement techniques. And we have to fight with corrosion effects, chemical side reactions, and so on. So my idea was to make a simplified analogy experiments, because I realized that when you swirl around a glass of wine to release its bouquet, for example, so this intuitive wave motion, if you just take a glass of water and doing this, I checked the theory of this sloshing dynamics and realized that this wave in the leading order is the same wave in the leading order destabilized by the metal pad rho instability. So here in the batteries, we have self-induced rotating Lorentz force-driven waves, while here in the wine glass, we have an externally forced wave motion. But if we here excite at resonance and do it carefully to have linear waves, we have perfectly the same wave motion. So this way we can imitate the wave as it results from the metal pad rho instability. And I constructed this quite simple experiment where I have an orbital shaker, which makes perfectly orbital or circular trajectories to excite waves in this cylinder. And here I realized a three-layer stratification where I sandwiched colored water between two silicon oils, which just represents a simple hydrodynamic battery model. And I applied different cups and tanks to realize different aspect ratios. And I was measuring wave motion with ultrasound transducers, because in future we plan to perform sloshing experiments with opaque liquid metals, maybe to make a combined experiments where we have some current, we apply a current and overlap it with some external forcing. So for this reason, I avoided optical measurement techniques. I applied simple ultrasound measurements. And the first qualitative result was that indeed I could recover both coupling regimes in the experiment. Here I have a scenario where I have paraffin oil over silicon oil, and at the top layer just air. So those interfaces here have very different eigenfrequencies. So I have a very small a here, small coupling parameter, and indeed I found the slow wave modes antisymmetric coupling motion. While here I have a stratification of two oils and water, where A is far more smaller to 1, and I found the symmetric wave mode. So this was qualitatively in agreement with my theory, but to be honest, the coupling here also depends on the forcing theory of the shaking table. And I found some complex transitions. So forced coupled wave motion is far more complex than a free coupled wave motion. So I couldn't do quantitative comparisons here, but it was still nice to see that we indeed have both predicted wave modes in this analogy experiment. Then I concentrated mostly on two-layer systems to study two different other effects which are very important to understand the stability of the batteries. I wanted to study, on the one hand, viscous damping, which highly affects stability onsets, and I wanted to study the influence of the contact line. So for that, as I already told, I could apply ultrasound transducers, 10 from both sides, to from the top and from below, allowing for simultaneous measurements of both interfaces. In this way, I could easily reconstruct the large-scale rotating wave motions. I could measure the frequency, the maximum elevation, as well as phase shifts I found between the shaking motion and the wave motion. So very simple measurement technique. And this way, I made a study where I modified the shaking frequency of the shaker and measured the maximum amplitude for different heights of the lower fluid. And you can see here typical resonance curves where the maximum peak reflects the eigenfrequency, the first large-scale rotating wave mode. And you can see curves for different layer heights. And you can see that if the interface is approaching the bottom wall, the maximum resonant amplitudes reduce drastically. So we have a far higher damping as the interface approaches the bottom wall. So we can say that shallow layers are kind of stabilizing. And this is a very important fact because from magnetohydrodynamic metal pad roll theories, we know that shallow layers are destabilizing, but they usually neglect viscous effects. And here I found the contrary results. So to really understand the stability, we have to account for both effects, the stabilizing effect due to viscous damping and the destabilizing effect due to Lorentz forces. And this also was more or less a qualitative result. And in 2019, Helmholtz-Zentrum has derived a theoretical formula for a two-layer damping rate to understand better predict the metal pad roll instability in cylinders. And I have measured then quantitatively the exponential decay and compared my measurements with his formula here for different layer heights. So as before, we have strong damping if the interface is close to the bottom or top wall, and not so strong damping in the center. And you can see a fair agreement here. It's when the interface was close to the top or bottom wall, the damping was so strong that I couldn't properly fit the exponential decay. So I have very large error intervals. And here, of course, the comparison is not so, so evident. But overall, I could, with this simple analogy experiment, I could validate a formula coming from a very different theory, which was made in the framework, not for a shaking experiment, but for a liquid metal or a two-layer aluminum reduction cell setup. So here, this was a second success of the analogy that we have the same wave in my shaking experiment to verify waves coming from Lorentz force-driven instabilities. And then I tried, of course, to validate my experiments itself, and I applied a sloshing theory from 2013 to my resonance curves. And I always found a strong shift. So this blue line here is the theory, and these are my measurements. And you can see that there is a strong mismatch between the peak frequency and the theoretical eigenfrequency. But I also found if I just shift the theory, then offsite resonance, I can perfectly match the experimental measurements. Of course, not at resonance, because this is inviscid theory, neglecting any dissipation mechanism, so it's diverging at resonance. But away from resonance, if I just shift the theory, then it was matching. So my idea was maybe some effects just disturbs the eigenfrequency, and it was confirmed. In fact, in all these measurements, I had fixed contact lines. So the contact line could not move freely along the cylinder walls. It was fixed. And there it is well known that these fixed contact lines drastically influence the peak frequency. And then I tried different things to reduce this effect. And for a particular measurement where I coated the sidewall with petroleum jelly, I had almost free moving contact lines. And for this measurements, you can see only a very small shift. So here, the theory is now almost perfectly agreeing. But unfortunately, this petroleum jelly was dissolving, and so this effect, I could measure it only for 30 minutes or so. Then the petroleum jelly dissolved, and the shift was increasing over time until I reached the initial state. So this was not the perfect solution. It is hard to control the contact lines, but it shows that on the one hand, the contact line has a strong influence, and usually in metal petrol theories, all these effects are neglected. All the theories assume perfectly freeing contact lines, but this, in my experiments, was more an exception than the rule. So usually I had either fixed contact lines or some contact line hysteresis, some even more complex dynamics where it was partially pinning, partially moving, so very complex, uncontrollable dynamics. So here, these results are stressed that we have to include these effects in future to describe the metal petrol stability in small mid-scale cylinders. Yeah, and after this experimental study, then I was unsatisfied that in the most interesting region, the theory by Reclavi was diverging. And at the same time, as I told you, Wietze-Harriman had derived viscous damping rates. So my idea was maybe I can include the viscous damping rates into the inviscid theory to close the resonance lines, resonance curves. So that was what I have done next. I have made a new theory, this time sloshing a force ray theory, where my two-layer cylinder here is elongated along a perfect circular trajectory of with some diameter ds and some angular frequency omega. And again, I formulated all boundary conditions. And here I have now this forcing term in Bernoulli equations. This is the most important term which makes the forcing. And from this, I could derive again some flow potentials where I have now amplitudes which are not free, which are directly governed by the forcing. And from this, you can derive a so-called modal system. So an infinite set of simple ordinary differential equations, where this omega here is a mode-dependent eigenfrequency, and zeta is a forcing term. And I just equipped this set with the damping rates derived by Wietze-Harriman, very complex formulas, but I just included a damping term into the modal system, allowing me to derive explicit solutions for the interface elevation, which now consists of a cosine and a sine contribution. It's a quite lengthy formula, but it's explicit. And I also could derive a formula for the phase shifts between wave and shaker, which is also of some fundamental interest because it can drastically influence the wave motion in forced waves. So I applied then this elevation formula to my experiments, and indeed I could close the resonance curves, and I found good agreement around the first wave mode, while my theory slightly overestimates the maximum amplitudes, because my experiment, I have also some damping contributions caused by the contact line, which is not reflected by the theory. But overall, the first mode is captured well, but I found a mismatch then around the second mode, where I qualitatively find the saturation I've seen in the experiments, but here is a clear mismatch, and I'm not so sure why for the second mode the results are not as good. The same for the phase shift. If I apply my my predicted phase shifts to the measurements, I found a good coincidence around the first mode and a clear mismatch at the second eigenfrequency. But again, I could at least describe the phase saturation, which is also an effect I've never seen before, which is only seen in multi-layer interfacial sloshing, not in free surface waves where you have orders of magnitude lower damping ratios usually. So I also compared this theory to some free surface measurements done by Bouvard in 2017. We intended to understand the mean mass transport coming along with this wave motion, which is also of interest, of course, for our liquid metal batteries, because a good mean mass transport will increase the mixing in the cathode. And here, I have to say, he made two different measurement series with silicon oil of different viscosities, but both measurements here are strongly weakly nonlinear around resonance. So I cannot, my theory cannot really describe the resonant wave motion. But interestingly, though it is here, even here it's subject to wave breaking, here it's weakly nonlinear, the phase shifts I derived can even, also it is coming from a linear model, can almost perfectly describe the measured phase shifts. And this is also interesting for a different application for so-called orbitally shaken bioreactors, which are used to cultivate stem cells, for example, or proteins. And these bioreactors are driven exactly by this rotational wave motion. And there it is known that this phase shift here has a strong effect on mixing. And here it seems that my linear model can even describe nonlinear phase shifts. So this was also in a different context a nice result for me. And finally, as an interesting, more fundamental result, my theory predicts the formation of spiral waves under the effect of damping. So here you can see the classic wave solution when there is no damping. And then I calculated just the shape of the wave, here normalized by the maximum amplitude for different damping ratios. And you can see that in the higher wave modes, you find a spiral wave structure, which is interesting from a fundamental point of view, because, for example, these waves have a chirality, they break the symmetry. These waves here don't know, or if you see these patterns, you cannot say is a shaker is rotating clockwise or counterclockwise. They always have the same shape, but these waves here have a chirality and look different if you shake the container clockwise or counterclockwise. So the direction of the shaking rotation is reflected by the patterns. So for me, it was a nice result because the spiral waves, similar spiral structures, are known from usually inherently nonlinear waves. We know from reaction diffusion systems or excitable media. In our heart, for example, we have spiral electric waves, or can have spiral waves, but I have never seen a linear spiral wave in this context. So I started with my colleague Stan Enders some more measurements to find them, or trying to find them in our experiments. And here, this is a very new result, still not yet published. You can say see a Schlieren image. So we place the camera on top and a dot pattern below the cylinder, and here you can see that a spiral wave motion is becoming visible as caustic, so displacement of the dots due to the wave elevation. And this was our first qualitative measurement confirming that spiral waves indeed exist, because the theory tells us that we find the spiral structures if we have strong damping and shallow layers, and also in the best case low bond numbers. So we can say that the theory told us where to look, and only thanks to the theoretical results we could find this spiral regime. I also have some more quantitative measurements where I here calculated from the Schlieren pattern the slope of the interface. And here's the theory, here's the experiment, and I will here increase the shaking frequency, and you can see the spiralization process increasing with increasing rotation frequencies. And here we are in a strongly overdamped state where all the wave crests are dying out in the center, such that only a ring of the outer crest is surviving. But I think the agreement between theory and experiment is remarkable, because the theory as experiment is, of course, there we have different damping mechanisms, we have interface contamination, not reflected by the theory, but the overall spiralization is well reflected. And I've just submitted a new paper on this spiral waves, which is not directly important for liquid metal batteries, but a nice fundamental result, because it's a new class of spiral waves, which to my best knowledge are not known before. All right, this was my last result I want to show you today. If you are interested into these topics, please feel free to ask some questions or to check my literature. So thank you very much for your attention. And of course, feel free to ask some questions. I'm happy to address them. Thank you.
Excellent. Thank you very much, Gerrit. Very nice presentations, results, and videos.
Thank you.
Great. So we are perfectly on time. So if there are any questions from the audience, we are ready for them. So feel free to ask.
Alberto, I have a question.
Yes, please, Professor Cuevas, go ahead.
Thank you. Gerrit, it was really very nice talk and very interesting. So your results are extraordinary. Congratulations. And well, I have a question about the first part of your talk. Yes. When you compare this potential theory with the numerical simulations. So your agreement is almost perfect. So the numerical simulation was done considering Lorentz forces, as far as I understood. So that means that in this particular case, you, well, I think you explained that, but I think I didn't got it. In this particular case, you don't have the effect of Lorentz forces, but I could like to understand why is this the case. Is because of this parameter that you then defined it?
So here, so again, the lines here, the points are the simulations where I solve the full magnetohydrodynamic system. So these periods are rising from the metal petrol instability driven by the Lorentz forces. And the lines here are my theory where I neglected the Lorentz forces. And the reason is that of course, I have two coupling mechanisms we can imagine. The first one is pure other pressure exchanges. If you have a rotational motion in one wave, it of course will affect the pressure of the other wave and cause some coupling. The other coupling mechanism is, of course, that when the upper wave is, for example, displaced, it will disturb the current distribution in all three layers. So also in the lower one, and this would be a coupling due to Lorentz forces. But obviously, and this is a finding, the pressure coupling highly dominates, and the other effect is negligible in all the cases I checked. So in particular, if both interfaces are close to each other, then pressure coupling is a dominant action here, and everything else seems of less importance. This is what the results here telling us.
Okay, yeah. Thank you very much, Gerrit. Very nice. Thanks.
You're welcome. Thank you.
We have enough time for more questions. Any questions from the audience, maybe? Well, Gerrit, I have a question. Well, now that we have this slide on the screen, why there is an error bar in the simulation? Is this because Norbert performed an average in time or something?
Okay, no, that's a good question. This regime here is a bit more complex than I told you. In this regime, I mostly found the symmetric this mode here, mostly, but sometimes I also had I found different instabilities in this regime. This was always dominating, but there was also maybe I have a slide for this, was also such an instability where I have an axisymmetric wave motion, and sometimes I had superpositions of both modes in this regime. And in this measurement with the strong error bar here, it is just that this measurement was, was disturbed by some secondary effects. So we can say here it was quite chaotic, while here I always found the anti-symmetric coupling. Of course, here are also sometimes error bars coming from, I averaged here's a period over maybe 30 or 40 rotations, and sometimes there are nonlinear or secondary effects, but overall it is following the theory.
Excellent, thank you. Any questions from the audience?
Alberto, I would like to make a question, if I may.
Yes, please go ahead, Professor Ramos.
I had a very impressive presentation. Thank you very much. I would like to ask you to go to, I think it was the first slide of your alternative experiment, I think you called it.
Yep.
The experiment try to mimic.
This one here or the next?
Yeah, that one, exactly. That's precisely the one I want. I didn't understand very well the experimental setup. If I interpret correctly this picture, you are rotating around the axis of the cylinder on the left hand, but on the right hand, where you have this wine glass, and the axis of rotation is off the center of the axis.
I see your question. Okay, sorry, this is a bit misleading, because here this is a small omega and this is a large omega, which means in my notation you cannot know this. This is just means this is the natural frequency rising due to Lorentz forces. So this is the eigenfrequency, while this omega is the forced frequency, which is arbitrary. And here I just want to, I just indicated that the wave is rotating around, driving by self-induced Lorentz forces. And here I'm shaking around a glass of wine, exactly like this. Maybe you can see. So there is no self-rotation, you're right, no self-rotation, only this rotation here.
Okay, now
This
that's
makes the same wave as on the left side.
thanks. That I understand now what you're saying. Now, if I may ask details on your experimental setup, because
Yes.
if I am not interpreting correctly, the experimental setup is not rotating around this axis of rotation. Am I right?
No, it is. It is exactly the motion I'm showing here, because the entire table here, this one, is making circles.
I see.
While container is fixed, there's no self-rotation. It's making this motion here.
So the axis of rotation is off the axis of symmetry of the cylinder, of the container. You have the axis. Can you see me?
Yes, yeah. No, but yeah, I now can see you. Yes.
Okay. This is the axis of rotation, and this is the axis of symmetry, and this goes around. Am I right?
Exactly. Maybe I have a picture. Let me see. Was it for the theory? Yeah, it should be like this. This part here.
Okay.
The cylinder is following the circle, but no self-rotation here.
Okay. Okay.
Yeah, it's like this.
But the distance between the two axes is very small compared with the radius or the diameter of the container.
Exactly. This is diameter ds here. And this is, of course, proportional to the forcing. And if I want to excite linear waves, then this must be small. In my experiment, I could continuously modify this distance. You can see here, this is the forcing term proportional to ds and omega squared. So if I just apply half of, if I reduce the diameter by a factor 2, I have factor 2 lower forcing in my force brake theory.
Okay. Okay. So it wouldn't be convenient for your purposes to use a larger distance.
No, if I use a larger distance, I excite nonlinear waves where and I have wave braking and other effects I don't want to consider in this study. This is also interesting for orbitally shapen bioreactors, but not, then I don't have an analogy anymore to the more peaceful metal petrol wave.
Okay, well, thank you very much for your answer. I'll stop here, and if I have the opportunity, I will ask some other questions later. Thank you.
Thank you.
Thank you, Professor Ramos. Gerrit, is it possible to relate this the coupling behavior that you have observed in the different batteries made with different metal alloys? Is it possible to relate the coupling behavior with some global parameters for the batteries, for the different batteries technologies? You show a table where you have the different alloys, and you identify that, for instance, for the calcium batteries based on calcium, they are not coupled, and for the based on lithium, they are strongly coupled. Is it possible to relate this behavior with some parameters of some batteries parameter?
Yes, so the coupling here, in particular in large-scale batteries, is mainly only the density difference of the lower and upper interface. Maybe we can see it here. Here's A. And if you have large cells, then this term here is dominating. So surface tension drops out, and it survives only the density difference between both interfaces. So this is then the most important parameter. And of course, oh, wrong direction. This regime here is desirable because here we don't have any short circuits, while this here is the worst regime provoking short circuits. And we have at some degree, we can influence maybe the density of the second layer of the electrolyte. Two, maybe if we are in this regime here, or in this regime, we can maybe slightly affect the density of the electrolyte to go into another better regime. This is the only thing we can do, but the coupling series independent of the geometry. I made the same model for rectangular cells, and as long as the lower top and bottom wall are parallel, it's always governed by this parameter, and we can only modify the density. And this is also, of course, we have to the electrolyte, we have to choose it to fit with the metals, so we don't have so much space or freedom to modify it. But maybe in some situations we can slightly affect row 2 in order to switch the coupling regime. This is the only point I see here.
Excellent. Great. Thank you. Okay. Are there any more questions from the audience? In these experiments with the UDV, where you follow the interface with the UDV probes, you mentioned that you used 10. You were able to reconstruct the interface, right? So for that purpose, instead of looking at the velocity, you were able to look at the echo signal?
Exactly. Yes, I directly track the echo. So usually UDV is applied, of course, to measure axial velocities. But here I'm interested in the elevation of the interface. So I can directly track the echo to reconstruct the wave amplitude and the interface motion.
Okay. Which interface did you follow? Both or just one?
In some cases, both, but I mostly shown here 2-layer experiments. Because the 3-layer experiments, as I told you, qualitatively nice, but they were very hard to control. Because if you look carefully here, you can see that, for example, in this case, here we have a fixed contact line, and here a free contact line, and this then it's uncontrollable. I cannot compare anything with a theory. This is one of the issues I faced. So the coupling mode survives, but these measurements, so even in 2-layer systems, I had problems to control the contact lines, but it wasn't possible in 3-layer systems. So for 3 layers, I only have qualitative results, unfortunately, because it's so hard to control 3 different liquids.
And just for curiosity, what were the velocity relations in the 2 layers? Did you remember those results? From UDV, you know, you can measure velocity profile, as you said, also, and the echo signal. So were you able to take a look on the velocity results, or it was?
You mean the vertical velocity, or which?
Yes, exactly. The vertical velocity.
Yeah, the velocity is directly correlated to the amplitude here in the phase velocity, of course. Okay. And you have always a higher velocity when the amplitude is higher. So in this case here, I had very comparable velocities, while of course in the magnesium antimony cell, where only is wave motion in the upper metal, there is no velocity at all in the lower interface. So this is easily, if you have formulas for the elevation and from the potentials, you can directly derive the velocity formulas.
Okay, great, thank you. Probably are there more questions from the audience?
Alberto, if there are no more questions, can I ask another one?
Yes, please, go ahead.
Related to the first part of your presentation, you showed us that there are symmetric waves that turn in certain direction. Is it possible? I suppose it's you can get the same sort of behavior, but going in the other direction. Am I right?
I probably didn't understand your question properly. Maybe let's find this. Which slide do you mean?
Yes, it's one of the first ones. You have that the wave is going in a symmetric way.
Yes.
It's turning in one azimuthal direction.
Ah, yes, yes, yes.
And I think that it can go in the opposite direction with equal probability. I mean, there's no way in which you can fix that.
No, that's a very interesting question. So this wave you see here, there's a rotation, direction of rotation is fixed by the direction of the current.
Okay.
If we consider, there's a nice theory which is proving exactly this fact. I have to go backwards. Yes, you can see it here. If you have a fixed current direction and a fixed BZ, then the product of both will here always govern the Lorentz force. And if we consider only the magnesium antimony battery, where we have only wave motion in the upper interface, we don't have this force. We have only this force here, always pointing inwards. And then you have here this way a counterclockwise rotation, I think.
Okay, so the Lorentz force is the effect that breaks the symmetry of the
Exactly. You can imagine that the wave is here pushed towards the back wall, and then you have the same wave as before, phase shifted by 90 degrees, and it's again then pushing against the side wall to the left in the next iteration cycle, if you want to say it. So the Lorentz force here breaks the symmetry. The direction is always governed by the sign of the product of B times the current density here.
Yeah. Okay. I understand. Thank you. And perhaps if I may ask one last question.
Sure.
In the, I think it was your last slide, where you showed us the experimental and theoretical. Yeah, that's the one. If you let it go, we can see that these spiral waves are forming. And I understand that in the theory, you don't have the possibility of instabilities of these waves because you're considering a linear theory. Am I right?
No, these waves are predicted by my sloshing theory. So where I described,
which is linear.
It's a linear. So yes, this is direct, completely following from linear solution. This is yes.
Exactly. So we do not expect these waves to be unstable, but in the experiment, of course, you have all kinds of interactions. And I was wondering if, under some circumstances, the spiral waves would become themselves unstable and incorporate more Fourier modes and become chaotic.
Yes, probably. If I increase the shaking diameter, I can definitely find a nonlinear or even chaotic regime. I haven't tried it yet because usually these spirals cannot be found, or the reason why they are not discovered before is that in comparable free surface sloshing experiments, so water would splash before at such high shaking frequencies, because for many reasons. One reason is that I have here an order of magnitude slower eigenfrequencies, so I can excite higher wave modes with slow frequencies, not possible if I just have a one layer free surface. And the second reason is that damping is far higher in two-layer systems. And this is, to my best knowledge, we have made the first interface sloshing experiment, at least under orbital excitation so far. So all the wave crests here are very small, just in the order of millimeters. So very stable linear waves, which are not possible to excite in water or in less viscous one-layer systems. But if I, and probably the damping rates are here so high that even with the highest shaking diameters we can apply, we won't touch the chaotic or nonlinear regime. But of course, as a physicist, for me, it would be very interesting to see if they can destabilize some other Fourier modes, or if we can see some chaotic behavior. It would be definitely a nice question to address in future.
Yeah, thank you very much. Very interesting, very beautiful results.
Thank you.
I will see at the chat. There are no questions on the chat. So any more questions from the audience? It seems that we don't have more questions. So, well, Gerrit, I really would like to thank all your passion and time for answering all of our questions.
Thank you very much again for the invitation. It was a pleasure for me, yeah, to share
Great.
my results with you.
Yeah, very nice presentations. We really enjoyed